Newton's second law tells us that the sum of the forces is equal to m times a. That's the mass times the acceleration. So we can use this relationship to determine the acceleration of a system undergoing different force interactions. So let's say we have the floor, and the floor is, in this case, about frictionless, so the coefficient of friction is 0. Now let's say there's a box sitting on the floor, and that box is being pulled to the right by a person. Let's say that the force the person applies is equal to 20 newtons. The mass of the box is 5 kilograms. And let's say that the angle that the rope makes above the horizontal, theta, is 10 degrees. So what is the acceleration of the box? Let's first start by drawing our free body diagram. This is a diagram to show all of the forces acting on our box. So in this case, we have a weight force straight down. We have a normal force from the surface onto the object. There's no friction in this case, but there is a pulling force, pull, due to the person at an angle above the horizontal there. So now I can sum the forces in the x direction and set that equal to ma. I can sum the forces in the y direction and set it equal to ma. Now in the x direction, let's look at what we have. There is the pulling force, and it has an x component. So I'm going to put a little subscript x there, and that's it. That's all we have in the x direction. So this would be equal to the mass times the acceleration in the x direction. Now, if I sum the forces in the y direction, there's a normal force that's up. There's a component of the pulling force that's in the y direction. And there's a weight that's in the opposite direction, so negative sign. And then equals ma, but in this case, the acceleration in the y direction is 0 because the box isn't moving up or down. It's in equilibrium in the y direction, but it's unbalanced in the x direction. So remember, when we have a force that is, or any kind of vector, that is at an angle, so if this is our 20 newtons, and this is our 10 degrees here, we can find this x component of our force. So this would be the force pull in the x direction, and it would be 20 times the cosine of 10 degrees, just like we've done before. So now let's substitute this expression into our force pull x. So we would have 20 times the cosine of 10 degrees is equal to the mass, 5 kilograms, times a. Now 20 times the cosine of 10 degrees is 19.7. And we'll divide that by 5. And then we'll get that the acceleration is 3.93 meters per second squared. Now let's try this one. We've got a box pushed across a rough floor. The coefficient of friction is 0.2. The push has a magnitude of 30 newtons at 30 degrees below the horizontal. The mass of the box is 10 kilograms. What is the horizontal acceleration of the box? So let's first draw a free body diagram to represent all the forces acting on the box. So here's my box, my little dot to represent the box. And the box would have a weight force acting on it because it's on the planet Earth. There would be a normal force because there is a surface. There's a push. Now this push is below the horizontal, so read below the horizontal. So when we look at this push, so we're imagining pushing it this way, but we're going to push it below the horizontal. So as I draw my free body diagram, I want to start my arrow on the body to show that this is my force push, and it is an angle below the horizontal there. Now there's also friction, and friction opposes the motion, so the force of friction would be to the left, and this is the force friction kinetic. So now that I've drawn my free body diagram, I can sum the forces. I'm going to sum the forces in the x direction, setting it equal to MAX. So there is an x component of the push minus the force of friction, and that will equal MAX. Now in the y direction, we're pushing this across a rough floor. So if you imagine this box is being pushed only to the right, and so it's balanced in the y direction. So that means that if I sum up all the forces acting on my box in the y direction, they should be balanced. So you can have a case where you've got a horizontal net force that is unbalanced. So this case would be a horizontal net force that's unbalanced, and you have a vertical net force that is balanced. So you can have unbalanced forces in one direction and balanced forces in another. So in the y direction, I would definitely have the normal force up and the weight force down, but notice that this push force over here has a component that is over. We took care of that in the x direction here, but it also has a down component there. So I'm going to put negative force push in the y direction, and I'm going to set all those forces equal to 0. So let's dig in. So this force push x would be equal to the push times the cosine of the angle from the trig that we've done before, minus the force of friction equals MA x. Now that's just an x subscript. So let's dig in further here, and the force of friction is mu times force normal, and that would equal MA sub x. Now the normal force is here, so I need to solve for this normal force. So if I add to the right side the weight and the force push that's in the y direction, that would be F sub g is mass times the gravitational field plus the push force that's in the y direction would be force sub p times the sine of the angle. So now I can make substitution. So I'll have 10 was the mass. Let's use 10 for g. The push was 30 newtons, and the angle was 30 degrees. That's our normal force that we'll substitute back in up here. So force push was 30 newtons times the cosine of 30 degrees minus the coefficient of friction was given as 0.2 times our normal force that we found, 115, is equal to m, which was 10 kilograms, times the acceleration in the x direction. So this would give me 2.98 when I do the left side here is equal to 10 times the acceleration in the x direction. So then we're going to divide by 10 and get that our acceleration in the x direction would be 0.298 meters per second squared. So that's one way to add friction to a sum of forces, and if the force applied is below the horizontal.